Assalamualaikum warahmatullahi wabarakatuh. This video is for CHM131 assessment lectured by Madam Nur Haslina, and our topic is chapter 6, which is chemical equilibrium. And my name is Muhammad Zaid bin Muhammad Zaini, student ID 2025873922, and next is my group member.
Hi, my name is Muhammad Ahmad Khalid bin Muhammad Faizi Asfa, and my student ID is 2025853098. And next is my group member.
Hello, my name is Muhammad Hani bin Muhammad Isham. My metric is 2025416836. Alright, let's move on to a new member.
Hi, my name is Muhammad Zain Shami Bisarizan, and my metric number is 2025805502.
Alright, so today I'm gonna explain what is equilibriums. So equilibriums occurs when opposing force or action are balanced. We can take examples of tug of wars. So basically there is no motions going on because the same force. So we call it no motions. We can call it chemical equilibriums is dynamic, constant motions. Alright, let's move on to the next slide. Alright, chemical equilibriums is dynamic, constant motions. The chemical equilibriums occurs when the forward and reverse reaction rate are equals. So for number 1, reactant react to form product. Number 2, product react to form reactant. Number 3, amount of each chemical stay the same. You can take examples of the formula. The reaction do not stop when equilibrium is reached. Constant motions. So look at the pipes. The water is running constant motions. Alright, let's move on. So the next thing is 3 characteristics of a system in equilibriums. So for number 1 is closed system. For number 2, the rate of the forward and reverse reaction are equals. Number 3, properties such as concentrations of reactant and products. Color are constant. Alright, next is what is K stand for? If K more than 1, reaction is product favor. If K less than 1, reaction is reactant favor. Alright, what C in Kc stand for? Is indicate that concentration unit of the reactant and the products. Alright, next. So, equilibrium's constant is Kc. Kc is the ratio of the equilibrium's concentration of product. We can take example of this formula we can use to solve this equilibrium constant Kc. Alright, next is equilibrium constant in terms of pressure, Kp. Reaction involving gas. The equilibrium constant is often expressed in terms of the partial pressure of the gas equilibrium constant. So basically, if it is involving gas, is equilibrium constant. So we got two formula right here. We can see to use it in pressure Kp. Alright, next is the reaction coefficient Qc. Reaction coefficient Qc is a mass action expression, just like the equilibrium constant Lc, except it is for a reaction at condition, not at equilibriums. The reaction coefficient is used to determine which direction the system will shift to the reach equilibriums. So for examples, we can take a look at this formula, where A, B, C, and D are molarity at any times. Alright, let's move on. So, for comparison of Qc and Qc, Qc equal K. So for number 1, the system is already at equilibriums. Number 2, it will not shift in either directions. If Q more than K, the system will shift to the left. And number 2, some product will be converted to reactant. If Q less than K, the system will shift to the right. And some reactant will be converted to products. Alright, that's all for me. Thank you.
Now it's my turn to explain the chemical equilibrium, which is how to calculate Kc, Kp, and Qc. So for example, is 2SO2 plus O2 forms into 2SO3, and at 700 K, the equilibrium constant, which is Kc, is 4 times 10 power of 4. So for example A, calculate Kp for the reaction. We're going to use the formula of Kp is equal to Kc in the bracket of RT and power of total N. So to get a total N, we need to moles of gaseous products minus moles of gaseous reactants. So for total N is 2 minus in the bracket of 2 plus 1, and we got a total of -1. So Kc is already given, which is 4 times 10 power of 4. And in the bracket is 0.0821 times 700, which is for the RT, and the power of -1. So we got RT of 0.017, and the Kp is 4 times 10 power of 4 times 0.017, and we got a total of 680 for the Kp. So for example B, given the initial concentration, which is SO2 is 0.20 m, O2 is 0.10 m, and SO3 is 0.40 m. So calculate Kc. We're going to use a formula which is Qc is equal to C power of C times D power of D divided by A power of A and times B power of B, where Qc is a reactant, which is on the top is reactant and the bottom is a product. So if we put the value, we got 0.40 in power of 2 divided by 0.20 power of 2 times 0.10. So after times, we got 0.16 divided by 0.004, and we got 40 for Qc. So for C, direction of reaction, since Qc is 40 and Kc is 4 times 10 power of 4, Kc is bigger than Qc. So since Qc is smaller than Kc, the reaction will shift to the right to form more SO3. Thank you.
Hi, and now I'm going to explain you guys about Kp equal to Kc RT power of delta N. And first thing we need to know is what is it and how to use it. Okay, as you can see here, Kp is a pressure, Kc is a constant, R is a radiant, T is a temperature, and delta N is a different number of mole of gas. Next one, equilibrium constant. You can see here C power of C, D power of D over A power of A, B power of B. Then this is the gas law, where P is equal to N power of V RT, where N power V is equal to concentration, P is a gas. And need to substitute it into the Kp like this. Then how to recognize Kc and delta N. Kp is equal to Kc RT delta N, where delta N is equal to C plus D minus A plus B. Right? So this is for example. We got here N2 plus 3H2, and at the right side we have 2NH3. If Kc is equal to 1.2 times 10 power of 3 and the temperature is equal to 400 Kelvin. And this is how we solve it. As we can see here, delta N is equal to 2 minus 1 plus 3, and we got -2. And just use the formula Kp is equal to Kc, that's Kc, and this is the radiant plus times temperature, and this is delta N. So we just solve it and we got. So that's all for me.
So today I'll be explaining about chapter 6, chemical equilibrium, Le Chatelier's principle. Let's go. What is Le Chatelier's principle? If a system equilibrium experiences a change, the system will shift its equilibrium to try to compensate for the change. So next, Le Chatelier's principle allows us to predict the effects of changes, such as constant, pressure, temperature, and catalyst. Next, a changing in concentrations only for gas and aqueous. Number 1, lower the concentration of remove some of the species. Number 2, the system will shift to produce more of that species. Number 3, increase the concentration or add some of the species. Number 4, the system will shift to produce less of that species. So next, if the concentration increases, the equilibrium shifts to the side that doesn't have X. And if the concentration decreases, the equilibrium shifts to the side that has X. Next, changing the volume or pressure only for gases. If the pressure is increased, the volume will decrease. The system will shift to the least number of gas molecules. If the pressure is decreased, the volume is increased. The system will shift to the highest number of gas molecules. Next, if pressure increases, the equilibrium shifts to the side that has less gas. If the pressure is decreased, the equilibrium shifts to the side that has more gas. Changing temperature. For every reversible reaction, if one direction is endothermic and the other is exothermic, for endothermic reaction, will absorb the heat from the surrounding. Increase temperature, then the reaction goes forward. Decrease temperature, then the reaction goes backwards. For exothermic reaction, it releases the heat to surrounding. If increases temperature, then the reaction goes backwards, and decrease temperature, the reaction goes forward. Next, using catalyst. A catalyst works by providing an alternative route with lower activation energy for forward and reverse reaction. Catalyst, it does not shift the position of an equilibrium system, does not change equilibrium constant, and only increase the rate of reaction. And next, factors that affecting equilibrium. Number 1, concentration. Increasing the concentration of reactants shifts the equilibrium towards product. Increasing the concentration of products shifts the equilibrium towards the reactants. Next, catalyst does not change the position of equilibrium. It only helps the system to reach equilibrium faster. Next, pressure or volume. For gaseous systems, increasing pressure will decrease the volume, and decreasing pressure shifts it to the side with more moles of gas. Last but not least, temperature. Increasing temperature favors the endothermic, and decreasing temperature favors the exothermic direction. And that's it. Thank you.